Hi everyone, my dear friends. Today we are going to discuss higher order linear differential equation. First, a differential equation of the type a naught into d power n into y by dx power n plus a1 into d power n minus 1 into y by dx power n minus 1 plus so on an into y equal to some phi of x. Okay, where a naught, a1, so on, an or either they can be constants or functions of x. Then we say that the differential equation is a nth order linear differential equation. Okay, first let us know about the meaning of dy by dx. Suppose I say a particle is moving in a some path y equal to f of x. Okay, I say a bead is moving in the curve y equal to f of x. So the meaning of dy by dx is, suppose at some particular point x naught comma y naught, I want to find out the particle velocity. So at that particular point, I can differentiate the given curve with respect to x. So I can find out slope of the tangent at that particular point to get the particle velocity. Okay. So dy by dx at x naught gives particle velocity at x equal to x naught. Here let us consider dy by dx. Okay. Dy by dx means the rate of change of y with respect to x. Okay. So here y is dependent variable, x is independent variable. We say conditions to be an linear differential equation. The differential equation should not contain the dependent variable and its derivatives in product form. Okay, we should not contain the terms like y into y dash, y into dy by dx. Okay, the degree and power of the dependent variable and all the derivatives must be 1. So again, linear differential equations are classified into two types. So first type is linear differential equation with constant coefficients. So second type is linear differential equations with variable coefficients. So a naught variable coefficients means a naught, a1, so on, an can be functions of x, should be functions of x. Okay. LD with constant coefficients. First, we talk about LD with constant coefficients. Consider LD of order 2. So I can write some a naught into d square y by dx square plus a1 into dy by dx plus a2 into y equal to some pi of x. Okay. So equation in this form is called as LD with constant coefficients of order 2. Okay. Here a0, a1, a2 are constants. So in so the meaning of d by dx is, we can write as simply operate with operator notation is as capital D. Okay. So dy by dx we can write as capital D of y. Capital D of y is nothing but dy by dx. So in the same way, d power n into y by dx power n is nothing but we differentiate y with respect to x n times. So you can write as d power n into y. So let us consider this equation as number 1. Okay. So in the same way, we can write d square y by dx square as capital D square of y. So here dy by dx can be written as d of y. Okay. This is a to y. Okay. So by chain rule, we can write as a naught into d square plus a1 into d plus a2 of y equal to pi of x. Okay, so consider this as f of d. F of d into y equal to some pi of x. We have written this same differential equation in terms of f of d into y equal to some pi of x. Now, LDE with constant coefficients is again classified into two types: homogeneous linear differential equation and non-homogeneous linear differential equation. In previous case, in second order linear differential equation, we got an equation that f of t into y equal to some pi of x. Okay, so that second order linear differential equation can be written as f of d into y equal to pi of x. Okay, here if pi of x equal to 0, we say that it is an homogeneous LDE with constant coefficients. If pi of x is not 0, we say that that linear differential equation is non-homogeneous linear differential equation. So now let's talk about the linearly independent functions. If two functions y1 or y2 said to be linearly independent functions, okay, then one function cannot be written in scalar form of scalar multiple of another function. Suppose if y1 y2 are linearly independent functions, so y1 not equal to lambda into y2. If y1 not equal to lambda into y2, so the y1 and y2 are linearly independent functions. Okay, so sin x comma cos x are linearly independent function. So you cannot write sin x equal to k into cos x, no. So that we can say sin x comma cos x are linearly independent functions. We have here a method to check whether two functions are linearly independent or dependent. So we check by Wronskian. Wronskian. So Wronskian of y1 y2 is nothing but that of y1 y2 y1 dash y2 dash. We have to remember this one. Wronskian of y1 y2 implies that of y1 y2 y1 dash y2 dash. If Wronskian not equal to 0, means determinant of this 2 into 2 matrix is not equal to 0, then y1 and y2 are called as linearly independent functions. Okay. If Wronskian of y1 y2 equal to 0, means such that determinant of this 2 into 2 matrix is 0, okay, then it is called linearly dependent functions. Then y1 and y2 are called linearly dependent functions. Okay. Next we move to, so we say that the number of arbitrary constants in an differential equation is equals to order of differential equation. Okay. Homogeneous linear differential equation. So we say that the general solution of homogeneous linear differential equation is called complementary function. Homogeneous means I have said already, f of d into y equal to some pi of x. We can write second order linear differential equation as f of d into y equal to some pi of x. If pi of x equal to 0, then it is called homogeneous LDE. Okay. So the general solution of homogeneous LDE is called complementary function. Okay. Next, to solve homogeneous LDE, first we got an equation f of t into y equal to 0, no? So now equate f of d equal to 0. First, we find the roots of the equation. Okay. Here a naught into d square plus a1 into d plus c2 equal to 0. Let us say m1 comma m2 are the roots. Okay. So we can write equation 1 as d minus m1 into d minus m2 into of y. Okay. So d minus m1 y can be 0 or d minus m2 into y can be 0. So uh, d of y means dy by dx that equal to m1 y. So here d minus m2 of y means um, dy by y equal to m2x, m2 into dx. Okay. Uh, so here you can see that integral dy by d equal to integral m1 into x. So you get y equal to e power c into e power m1x. So I treat e power c as c1. Okay. And in similar way, we get y equal to c2 into m e power m2x. So these both are solutions of that given equation, that homogeneous linear differential equation. I will say y equal to c1 into e power m1x plus c2 into e power m2x is also a solution. So their linear combination is also a solution of that second order homogeneous linear differential equation. So why it is, why it happens so? I will say for you with an example. Okay, let us consider an second order linear differential equation. Okay, so d square y by dx square plus here b into dy by dx plus cy equal to 0. Okay, I say y equal to f of x and g of x are solutions. I consider that's it. Okay, here I substitute f of x in place of y. So if f of x and g of x are solutions, we can substitute, we can replace y by f of x once, and we can second time I will replace y by g of x. Okay, if I replace y by f of x, I will get, we have to differentiate 2 times f of x. We get f double dash of x plus b into g dash of x plus c into f of x. Okay, if y equal to g of x is solution, again I replace y by g of x. So I can get g double dash of x plus b into g dash of x plus c into g of x equal to 0. I say this equation as 3 prime. Okay, so I will consider a function h of x. I say g of x plus f of x something. Okay. Um, if I add 2 prime and 3 prime equations, okay, I will get f double dash of x plus g double dash of x plus b into f dash of x plus g dash of x plus c into f of x plus g of x equal to 0. So if you replace y by h of x, you get h double dash of x plus b into h dash of x plus c into h of x equal to 0. If h of x is a solution for this differential equation, you get the before I said no that equation. So you replace h of x by f of x plus g of x. If you differentiate f of x plus g of x 2 times, you get the same answer as this. Okay, plus b into f dash of x plus g dash of x plus c into h of x. No, h of x is nothing but f of x plus g of x. So h of x is also solution for given second order linear differential equation. So if y1 comma y2 are solutions, I can say their linear combination is also a solution. So in this manner I can say their linear combination is also a solution. So first case, if m1 comma m2 are real and distinct, I can write directly as c1 into e power m1x plus c2 into e power m2x. Okay. This is the same way. First we write auxiliary equation. Auxiliary equation is nothing but you replace We replace d by m. Okay, m square plus 5m plus 4 equal to 0. We get m1 comma m2 as the roots minus 4 comma minus 1. So our solution is c1 into e power minus 4x plus c2 into e power m2x. No, m2 is nothing but minus 1. Okay, you can replace m1 comma m2 by minus 4 comma minus 1. You get the solution as this one. Second case, if m1 comma m2 both are real and distinct, we will write as c1 plus c2x into e power mx. So if second order second order uh, second second order linear differential equation is given, we write c1 plus c2x. If third order is given, if the third order if the third order equation possesses all three roots equal, so then we write solution as c1 plus c2x plus c3 into x square into e power mx. So if fourth order linear differential equation is given, if it possesses all the four roots as equal, then we write c1 plus c2x plus c3x square plus c4 into x cube into e power mx as solution. So we move on to the next. So if the roots of auxiliary equations are complex, suppose if m1 comma m2 are complex, all uh, complex roots occurs in conjugate pairs. Okay. Uh, if m1 comma m2 are alpha plus or minus I beta, I write y equal to the solution as y equal to e power alpha x into c1 cos beta x plus c2 sin beta x. Just remember that is enough, my dear friends. Okay. Suppose I will consider nth order linear differential equation a naught into d power n. We write in operator form. Okay. After operator form is nothing but we replace d by dx by capital D. Okay. Let the roots of auxiliary equation be m1 comma m2 comma so on m. In case 1, I will take all the roots as distinct. Okay. So I will write the solution as c1 into e power m1x plus c2 into e power m2x plus c3 into e power m3x plus so on cn into e power mn into x. So it is the repeated case. Okay. So if I take all the roots as equal, m1 comma m2 comma so on mn are equal, I will write the general solution as c1 plus c2x plus c3x square plus so on cn into x power n minus 1 into e power mx. Okay. Next, m1 comma m2 comma m3 are real and distinct. m4 comma m5 comma m6 are three roots which are real and equal. Okay, m7 comma m8 are alpha plus or minus I beta. m9 comma m10 are p plus or minus I. So first three roots are real and distinct. I will let as same procedure. Okay, c1 into e power m1x plus c2 into e power m2x plus c3 into e power m3x. Okay, next I say here m4 comma m5 comma m6 are equal roots. I consider them as m. So we can write as c4 plus c5x plus c6 into x square of e power mx. So m7 comma m8 are complex roots. No, we say that e power alpha x into c1 cos beta c7 cos beta x plus c8 into sin beta x. m9 comma m10 are p plus or minus iq. We say them as e power px into c9 cos c9 cos qx plus c10 cos qx. Now let us discuss non-homogeneous linear differential equation. So in previous case, f of d equal to f of d into y equal to some pi of x. Okay. If pi of x is 0, we are saying that it is a homogeneous LDE. If pi of x is not 0, we are saying that it is a non-homogeneous LDE. So we get the solution of non-homogeneous LDE by adding both complementary function and particular integral. Okay. There is f of d into y equal to pi of x. No? Particular integral is nothing but 1 over f of d applied over pi of x. Okay. That will be We will be discussing about that in detailed manner. Please wait some time. Okay. PA cannot PA cannot particular integral. We have to remember one point. Particular integral cannot contain arbitrary constants. Okay. So if y equal to pi of x by capital D, we should not say by D. So operator one over D applied over pi of x. 1 over D is called inverse differential operator. So it is nothing but pi of x by capital D means integral pi of x into dx. But we don't write constant. Okay. In particular integral we never write constants. So we move on to the next. So we have like this, suppose y equal to pi of x by d minus a. Okay. We just cross multiply it. D of y minus small a into y equal to pi of x. Here capital D means dy by dx. Okay. Capital D of y means dy by dx minus a into y equal to pi of x. We know that it is linear differential equation. Solution is obtained by integrating factor. So y into solution of this differential equation is y into integrating factor is equals to integral of integrating factor into here RHS we have pi of x into dx. Okay, integrating factor is nothing but e power integral p of x dx. P of x is nothing but quotient of y. Okay, integrating factor e power integral of minus a into dx equal to e power minus a is constant, we get outside integral 1 dx is x. So this particular integral can be obtained in this manner. So we get y into e power minus ax equal to integral of e power minus ax into pi of x dx. This is pi of x. I written in very short manner. Okay, no problem. Similarly, we can get one operator 1 by d plus a over pi of x is e power minus ax into integral e power ax into pi of x dx. So how to find this? In the same manner, my dear friends, uh, we just cross multiply this capital D of y plus a into y equal to pi of x. Same. Again we get linear differential equation. Here integrating factor is e power integral a into dx. Okay. So in this way you can get this. So if we have non-homogeneous LDE in this manner, d square minus 3d plus 2 into y equal to e power x. Okay. To find complementary function. So first we replace d by m. Okay. M square minus 3m plus 2 equal to 0. We get m1 equal to 1 and m2 equal to 2 as the roots. Okay. Here complementary function is the general solution of homogeneous LD. Okay. So C1 into e power 1x plus C2 into e power 2x is the C2 into e power 2x is the complementary function. Now we have to find particular integral. So particular integral. So to find particular integral. So 1 comma 2 are the roots of auxiliary equation. So we write e power x e power x applied over d minus 1 into d minus 2. Okay. Here again in numerator 1 we can write as d minus 1 minus of d minus 2. Okay. On partial fractions we can get is split in partial fractions. Okay. E power x by d minus 2 minus e power x by d minus 1. So it is in the form of e power x by d minus a. Okay. I showed in the previous slide. We have here formula no pi of x by d minus a. Here pi of x is nothing but e power x. A is nothing but in first one a is 2 and in second one a is 1. So we can get particular integral also directly. So the solution of given non-homogeneous linear differential equation is CF plus PA. That's it. Here we have some special cases. So my dear friends, if pi of x equal to e power some constant a into x, okay, we have particular integral. Some I say e power x by f of d. So to find particular integral for this one, I replace d by a. Here x quotient is a, so I will replace d by a. If f of a is not equal to 0, then this particular integral value is e power ax by f of small a. If suppose in case f of a is 0, means a is root of auxiliary equation. Okay, then we have to write x into e power ax by f dash of d. Okay, so here x is out of the differential operator. Okay, x into we write e power ax by f dash of d. We replace d by small a. If f dash of a is not 0, we write x into e power ax by f dash of a as particular integral, and so on and so forth. In this fashion, we write suppose if I have if I have suppose I am saying d cube y by dx cube minus y equal to e power x plus 1 whole square. We write in operator form. Okay, capital D cube minus 1 into y equal to e power 2x plus 1 plus 2 e power x. So auxiliary equation is m cube minus 1 equal to 0. So solution of this differential equation is CF plus PA, complementary function plus particular integral. So I can write this m cube minus 1 as m minus 1 into m square. Okay. Um, so I get one root as 1 and remaining two roots as omega comma omega square. So I can write complementary function as c1 into e power x plus e power minus e power alpha x. No, alpha is here minus 1 by 2. E power minus 1 by 2 x into c2 cos, here beta is root 3 by 2. Root 3 by 2 x plus c3 sin beta x. Okay, I got the complementary function. Now I have to find particular integral. So I can apply. Now I want particular integral. We are having e power 2x by d cube minus 1 plus 1 by d cube minus 1 plus 2 into e power x by d cube minus 1. Okay, I say this as pi1, this as a pi2, this as pi3. Okay, if we have e power ax by f of d, we replace d by small a. Okay, here we replace d by 2. Okay, pi1 is nothing but e power 2x by 2 cube minus 1. pi2 is nothing but 1 into e power 0. I write as 1 into e power 0x. So it is again in the form of e power x by f of d. Okay, here I replace capital D by 0. So here pi3 2 into e power x by d cube minus 1. If I replace d by 1, so it is going to become 0. Okay, so I can write this as x into e power x by f dash of d. F dash of d is nothing but 3d square. Okay, again we replace d by 1. Okay, we get directly particular integral as e power 2x by 7 minus 1 plus 2x into e power x by 3. Okay, this is the particular integral. We get, so now solution is cf plus pi. Cf plus pi is nothing but